Hello students, today we are going to discuss about analysis of strain. A body which is subjected to compound stress is in general also subjected to compound strains. In a body under the two-dimensional strain conditions, the strain condition on any particular plane of at any inclination can be analyzed as we are going to discuss today now. Let's first talk about the direct strain in a given direction due to normal stresses. So here in figure you can see a case in which two-dimensional stress state is shown. So stress is being applied in the direction x, which is sigma x, normal stress, and there is another normal stress perpendicular to the direction of x, that is y. A stress of magnitude sigma y is being applied. So because of this two-dimensional state of normal stresses, we want to find out the strain in a particular direction, let's say angle theta, from the x-axis. Now we will analyze it in such a way that we have our block ABCD, which is subjected to sigma x and sigma y, and due to the application of stresses it will deform to the block AB1 C2 D1, because we know that these stresses are tensile in nature, so they will increase in size both in x side and y side, and that's why our original block ABCD will transform into AB1 C2 D1. Okay, so the length AB has increased from AB to AB1. Our height AD has changed from AD to AD1, or BC has changed to B1 C2. So this is the deformation which has taken place. Now because of the stresses, we can find the strain values in direction x or direction y. So strain in direction x can be obtained by the stress value sigma x and sigma y, and it can be expressed as epsilon x equal to sigma x by E minus mu times of sigma y by E. You must have remembered the nu is the Poisson's ratio. So we have already talked about that. So with the help of Poisson's ratio, we can find out the strain in the direction x. So this is because of the stress in the x direction, so sigma x by E, and because of the application of tensile stress in a direction perpendicular to x, there will be reduction in the strain value by the magnitude of mu times of sigma y by E. Okay, so that is the second component here appearing. So that is sigma epsilon x. We can similarly define the value of epsilon y. It will be simply sigma y by E minus mu times of sigma x by E. Now the diagonal AC, which is at an angle theta with the AB, we can determine the stress in the diagonal AC. So original length of the diagonal was AC, which is shown here. After deformation it get converted to AC2. It has increased in its length. So the deformation has AC2 minus AC, and the strain in the direction theta will be, which is called as epsilon theta, will be given by AC2 minus AC divided by the original length of the diagonal, that is AC. So that you can say as a diagonal strain also, and its value will be AC2 minus AC divided by AC, which if we simplify will give us AC2 equal to AC multiplied by 1 plus epsilon theta. Now from the triangle AB1C2, this is the triangle I am talking about, AB1C2. So this triangle, because of that, we can see that AC2 square is equal to AB1 square plus B1C2 square. Okay, so for AC2 I am going to substitute AC into 1 plus epsilon theta, so it becomes AC square into 1 plus epsilon theta whole square. The AB1 distance can be given by AB plus AB times of epsilon x, so that's why it is AB into 1 plus epsilon x. Okay, so therefore AB1 can be expressed with the help of strain epsilon x as AB into 1 plus epsilon x. Similarly, B1 C2, the height of the block, the new height of the block, can be expressed in terms of BC into epsilon plus y. So we substitute this value over here and we simplify it. So we will open this. So 1 plus epsilon theta whole square will become 1 plus 2 epsilon theta plus epsilon theta square, and similarly 1 plus epsilon x whole square and 1 plus epsilon y whole square. But we will neglect the square powers of epsilon theta, epsilon x and epsilon y, because they are very small quantity, so their square will be even further small quantity. So finally we will get the remaining expression as shown here, which we can open it and simplify it like this. Now because AC square, if you look at the triangle ABC, so AC square is equal to AB square plus BC square, so AC square will get cancelled with the AB square plus BC square, and you can calculate the value of epsilon theta as epsilon theta equal to AB by AC whole square into epsilon x plus BC by AC whole square into epsilon y. Now from the triangle ABC, because AC is at angle theta with AB, we can find that AB by AC is nothing but cos theta, and similarly BC by AC is nothing but sin theta. So when we substitute it, we'll get this equation 1, which gives the relation between the diagonal strain theta or strain in any direction theta with the strain in the direction x and y and angle theta. Okay, so if you know the strain epsilon x, if you know the strain epsilon y, if you know, you can determine the strains at angle theta from the x-axis, and you know the epsilon x, epsilon y because you have calculated them using these two expressions from sigma x and sigma y. You can always calculate the value of epsilon x and epsilon y. Now let's calculate the direct strain in the case when there is only shear stress acting. So the previous case was the case when there was only normal stresses were acting in both x and y direction. Now in case when there is only shear stress is present on the system, how we can calculate the direct strain in a particular direction theta. So we have here we have the block ABCD. Because of the shear stress tau which is being applied, it will get deformed to the shape ABC1 D1. It will become a parallelogram. Okay, now let's do some construction. Let's draw a perpendicular from C at diagonal AC1, so that is a perpendicular CL which is drawn on the diagonal AC1. Now we know that the shear strain is defined as the tangent of the change in the angle between the two originally perpendicular axes. Okay, so I haven't shown it here in this figure, but this is your angle phi, okay, which defines the tangent of this angle. I can write it here. This is phi angle. So the tangent of the phi defines the shear strain. Okay, so as shear strain tangent phi is very small, so this is, we can say, is approximately equal to phi. So what is the value of tangent phi? If you look at the triangle BCC1, so the tangent of the phi will be CC1 divided by BC. So I am talking about this triangle here, BCC1. So tangent of phi will be CC1 divided by BC, and this will be approximately equal to phi. So from this we can obtain that CC1 is equal to phi times of BC. Now the direct strain in the direction A to C will be the new length AC1 minus the original length AC divided by AC. So epsilon theta, or the direct strain in direction theta, will be AC1 minus AC divided by AC. AC1 minus AC, if you look here, this is AC1, this is AC1 and this is AC. So if you make a difference of these two, this will be simply equal to near about C1L. So that is what I have written here. So AC1 minus AC will be approximately equal to C1L divided by AC, and if you look at the triangle CC1L, that's a small triangle there which has the angle CC1L defined as theta. So that will give you the C1L value as CC1 cos theta. So that we substitute here. So this becomes epsilon theta becomes CC1 cos theta divided by AC. From here we know that CC1 can be written from the equation 1 as 5 times of BC. So you substitute here 5 times of BC, and BC by AC, that means from this triangle ABC, the BC by AC is nothing but sin theta. So that gives you the value of epsilon theta as 5 times of sin theta cos theta. Remember what is phi? Phi is the shear strain, okay, whose approximate value will be given by tangent of phi or equal to CC1 by BC. So using this we can find the value of strain in the direction theta if we know the shear strain value phi. Now imagine a case in which we have all three together, sigma x, sigma y and tau xy, all three acting together. Then we simply have to superimpose the equation 1 which we determined for the only case of sigma x and sigma y, and equation 2 which we obtained only for the case of tau, and add them together so that we can obtain the equation for the case when both shear strain and normal strains are acting. So that gives us this equation, epsilon theta is equal to, this part is coming from the normal strain equations, epsilon x cos square theta plus epsilon 1 psi square theta, the equation first, and this is coming from the equation second. So this is simply superimposition of these two terms. We can express the cos square theta and sin square theta and sin theta cos theta in terms of cos 2 theta and sin 2 theta like shown here, and which after simplification will give us this equation 3. So this is our equation 3, which gives us the strain at an angle theta if you know the value of strain in the direction x and y as well as the value of shear strain phi. Now this epsilon theta will be maximum or minimum when if you differentiate it with respect to theta and equate to 0. Equation 3, if you differentiate it with respect to theta and equate to 0, this will give you the maximum or minimum value of epsilon theta. So for this purpose, if you differentiate it, the differentiation of the first term here will be 0. Cos 2 theta differentiation will be minus 2 times of sin 2 theta. So 2 and 2 will get cancelled out. This will give 2 cos 2 theta, again 2 will cancel out. This will be the remaining expression, which is going to give us the angle of the plane where the strain theta, epsilon theta will be maximum or minimum. So that angle will be tangent of 2 theta equal to phi divided by epsilon x minus epsilon y. So this is the angle of the plane of principal strains, because at the principal strains your direct strain will be either maximum or minimum. So there will be two mutually perpendicular plane. The first plane will be given by theta is equal to half of tan inverse phi divided by epsilon x minus epsilon y, and the other plane will be at 90 degree to it. So you simply have to add the value of 90 to this expression. Now you can obtain the principal strains, that means the maximum or minimum value, by finding the value of theta and finding the sin 2 theta and cos 2 theta. You can use this expression for this purpose and simply make a triangle here. You say okay, this is phi, this is epsilon x minus epsilon y, so this is under root of phi square plus epsilon x minus epsilon y whole square, and using this you can find the value of sin 2 theta. This angle is 2 theta, okay, so sin 2 theta and cos 2 theta, and you substitute it over here in this expression. So when you substitute it over here, you will get the maximum and minimum value as shown of equation 5. So that will be epsilon theta is equal to half of epsilon x plus epsilon y plus minus half of under root of epsilon x minus epsilon y whole square plus y square. This is very similar to what we did in the case of principal stresses. You must please go through that. You will find that similar exercise we have done in the case of principal stress also. So by using the equation 5th, we can find the first principal strain epsilon 1 and second principal strain epsilon 2. One will come with the positive value here, another will come with the negative value here. So this is the expression for our principal strain. Now if you already know the value of principal stresses, you can straight away determine the value of principal strain rather than using equation 5. So you can use it for equation 6. That means epsilon 1 will be sigma 1 by E minus mu times of E into sigma 2 plus sigma 3 and so on for the epsilon 2 and epsilon 3. Now strain energy can be determined if you have if you know the value of epsilon 1, epsilon 2 and epsilon 3. So you can determine the strain energy. You must have remembered when we discussed about the stress strain diagram, I told you that the area under the stress strain curve, that means that straight line curve basically gives you the strain energy. So because the triangular area was obtained, so that's why it was half times of sigma times of epsilon. So from that stress strain diagram we obtained that. So now you have three expression of sigma and epsilon. So the strain energy stored will be half of sigma 1 epsilon 1 plus half of sigma 2 epsilon 2 plus half of sigma 3 epsilon 3. If you substitute the value of epsilon 1, epsilon 2 and epsilon 3 from equation 6 in this equation, you will obtain the strain energy as shown to you here. Now obviously the expression for the principal strain equation 5 is very much similar to what we obtain for the case of principal stress. So we can use the Mohr strain circle also to determine the value of strains, principal strains and their angle also. So let's follow the same theory that we did for the case of principal stress. So if you look here in this figure, we will plot the value of OA, value of this point A from the origin, OA as epsilon x. We will plot the value of OB as epsilon y. Then we will draw a perpendicular at point A and point B. Okay. First we will locate the center of this A and B, that is epsilon x plus epsilon y by 2 from the origin. So you locate the C and then you draw the perpendicular at point A and B, which will be equal to phi by 2 and phi by 2 distance. So you cut the value of AD and BE from there, and then using the center C and taking the radius as D, CD, you draw a circle there which will cut the OX axis at the point G and F, and therefore the OG will give you the value of epsilon 1 and OB will give you the value of epsilon 2, and the angle DCA will be equal to tangent the angle 2 theta. So this is very much similar to what we did in the case of Mohr circle for the stresses also. Now we can prove it also in the similar way that we did for the case of principal stresses. So here you can see that the value of OC, because OA is epsilon x and OB is epsilon y, so the OC will be equal to epsilon x plus epsilon y by 2. So this will be how we will locate our center. And the distance CA will be equal to CB, and this will be simply epsilon x minus epsilon y by 2, because AB is epsilon x minus epsilon y. So that's why CA which will be equal to CB will be equal to epsilon x minus epsilon y. Now if you look at the triangle CAD, this is the triangle I am talking about. If you look at this triangle CAD, so CD will be equal to under root of CA square plus AD square. Now CA is equal to epsilon x minus epsilon y by 2. So that we substitute here. AD is nothing but the phi by 2 that we have taken, half of the shear strain. So that gives me the value of CD as half of under root of epsilon x minus epsilon y whole square plus phi square. So that is the radius of the circle. So because it is radius of the circle, so CD will be equal to CG. It will also be equal to CF. So from this we can define the value of OG as OC plus CG. So you substitute for OC from here, so that comes here, and for CG you substitute from here, and you will get the value of first principal strain epsilon 1. Similarly, you can define OF as OC minus CF, and when you substitute the value of OC and CF, you get the value of epsilon 2, or the second principal strain. And the tangent of 2 theta that we obtained from the triangle CAD will be given as AD by AC, because AD is equal to phi by 2 and AC is equal to epsilon x minus epsilon y by 2. So that gives you tangent of 2 theta is equal to phi divided by epsilon x minus epsilon y. That is our actual formula for tangent of 2 theta. So by this method more circle, we can again determine the value of principal strains and their angle. Let's look at this small example, and here the things are given in a different way. So you have a material which is subjected to two mutually perpendicular linear strains along with the shear strain. So you have epsilon x, you have epsilon y, and you have a tau xy. All three are given to you, all three are being applied. What is given to you is the value of principal strains. So that is known to you. You have given the first principal strain as 0.001 compressive, and you are given the second principal strain as 0.003 tensile. So the principal strains are given to you. You don't need to determine the principal strains. They are given to you. One of the linear strain, that means epsilon x, that is being applied is given to you. That is 0.00025 tensile. You need to determine the second linear strain, that is epsilon y, and you need to determine the shear strain, that is phi. So from this you know the epsilon 1, epsilon 2, and you know the epsilon x. What is need to be determined is epsilon y and phi. Now how will we construct the circle or more circles in this case? First of all, because you are given the principal strains value, so you can easily locate the value of point A, that is OA, you can mark equal to epsilon 1. Second thing you will do is mark OB, because it is a compressive in nature, so you will draw it from the left hand side of the origin. So you mark the point B. So once you got the point A and point B, it is very easy to find their center. So that will give you the point C at middle of it. After getting the center, draw a circle using the radius of CA. So you will get the circle. So after getting the circle, we will first mark the value of epsilon x. So epsilon x is equal to D. So you will locate the point D. So point D is given here. So you locate the position of D from origin. So that is the equal to epsilon x, because this value is given to you. From D you will draw a perpendicular which will cut the circle at point E. So you will get the position of E. You will join the E to C and extend it further so that it will cut the circle at point F, and from point F you will draw again a perpendicular on horizontal axis which will cut the horizontal axis or x-axis at point G. Now because you know that OD is equal to epsilon x, your OG will be equal to epsilon y. So whatever scale you have chosen, use that scale and convert it back to the strain values, and you will find that the epsilon y value will be calculated as 0.005. You can measure the value of DE from the by using the scale. Again convert it whatever strain values you have chosen. So DE will be equal to 5 by 2. From this you can get the value of shear strain as equal to 0.000264. So that is how you can calculate the value of shear strain. Now this brings us to the end of our chapter of the principal stress and principal strains and more circles. There are plenty of numericals which are given in your book. Please try to solve them, both the solved and unsolved examples.